Okay, everybody, let's go on number 12 from the day 8 and 9 homework. Sure, red. All right. So again, we are trying to show that we're 1 to 1. And of course, this thing is a quadratic function, so it would not be 1 to 1 if it weren't for this domain restriction. So they've given us a domain restriction. But the function without that domain restriction would have its vertex at -4, -5. So like here-ish. And then it's stretched vertically by a factor of 3. So what if this is -4? You guys could be building a table of values. I would recommend that. So -4 is our vertex, and it's going to give us -5. Then if we push to the right by 1, go to -3, then we get 1 squared is 1 times 3 is 3. 3 minus 5 is -2. So it would be here. And we can use symmetry to just reflect that over. So it would also be at -2 at -5. And we could go to -2. That's going to give us 2 squared 4 times 3 is 12. Take away 5 is 7. So at -2 we'll be way up at 7. So what happens, of course, is we know that this factor of 3 is stretching us vertically. That's why this graph is growing really, really quickly. And so looking at this, of course, it's a parabola. So it's not 1 to 1. But that's why they've included this restriction. They're saying we only want the x's that are less than -4. So again, we're looking at the left-hand side rather than the right-hand side. So really, after spending all that time graphing it, we don't actually want this half. We only want that left-hand side. And then we can get down to business. Forget the table of values. I do want you to think about the domain and range. The domain was given to us. It's -infinity to -4. The range, you have to think about a little bit yourself. It's going to be 5 to infinity. The graph hasn't been reflected. It's just been chopped in half. So we're still going to get the same values from the vertex up. So -5 to infinity. Hopefully that's what I said before. But there's the domain and range for the original function. And now we know that it is 1 to 1. So if we find the inverse will be a function. So let's find that inverse algebraically. We'll just take the original function and switch the x and y variables. So that means f of x becomes x becomes y. And then we just want to solve for y. So it certainly seems like we're going to add 5. And then we're going to want to get rid of that 3, either by dividing by 3 or multiplying by a third. Multiplying by a third would be my preference. From here, you can see we're going to want to take the square root on both sides. So that'll generate a square root of 1/3 x plus 5. That equals y plus 4. So to get your final answer, you'll just subtract 4. So there's our inverse function. But before you pat yourself on the back, there's something a little bit fishy here. So let's go to Desmos. And our original function was 3x plus 4 squared minus 5. So it's that, but remember, it's not really that. It was on a restricted domain. So we can do that in Desmos. You just put your restrictions in braces. And so we said we wanted only those x's that are less than or equal to -4. And then you see the graph gets restricted to just that half. So whatever, big whoop. Now let's put in our inverse function that we found. See how that goes. That's from here. So it was 1/3 x plus 5 minus 4. And this is all under a radical. Oh, come on, dude. All right, whatever. Okay. So looking at this, looks real good, right? Looks perfect. We could graph y equals x. That's supposed to be our mirror line. And hopefully you can tell that nope, something's off. Looking at this, these things are not reflected images of one another. And so what's the problem? Well, the problem is we started with the left-hand side of a parabola. When that left-hand side gets reflected, it should be the bottom half of our radical function. So we need to just know that this is not really the function we want. The function we want is, boop, the opposite. We want the bottom half. So you have to know to put that negative on it. There's not like a rule of algebra necessarily that keys you in. You just have to understand that to get the inverse of the left-hand side of a parabola, you're going to want the bottom half of the parabola defined by the radical function, not the top half. So you have to make that change. Maybe this was a really long-winded way to explain that, but hopefully the visual and all that will really make it stick out in your head, that you have to think about which half of the graph you started with. And again, of course, there's another way we could have done this other than going to Desmos and looking at the graph. We should know that for this radical function, its domain would be -5, and then only the things greater than -5. And that checks out because we're supposed to get our domain from the original function's range, and those match, so that's great. But the range, if we left this thing as written, and if we didn't have a negative, then our graph would be the top half, and so -4 would be our min, and we'd be getting everything bigger than that. Our range would have been -4 to infinity, but our range is supposed to come from the original function's domain, which is -infinity up to 4. So that clues you in again that this function needs to be reflected over so that its range will be this function's domain. So super important that you don't forget that. If you guys give me the wrong domain, that's going to be a big deal, and big points deducted. So don't. So there's that. Everybody good? I hope so. What's left? Just to do the composition, right? Yeah, just to do the composition. Okay, so I'm running low on room, so we'll just scroll down. Okay, hopefully I can, I don't know. Here's the top of my screen. Where's the bottom? This is the bottom. Here's the left, and here's the right. All right, so I'm not going to go outside of that window. Whatever. Now, we can do our compositions. We can put a little divider line down the middle, because we know on one side we need to be doing F composed with F inverse. On the other side, we need to be doing F inverse composed with F. And the two functions are what? I don't even remember anymore. So the quadratic, which was 3x, there's like a 5 and a 1 in there somewhere. Oh, x plus 4 squared minus 5. Cool. And the inverse we found was negative root 1/3 x blah blah blah. So there's the two functions. So over here, we're going to do, we're plugging in the inverse function into the original. So it's going to be 3 times parentheses bracket plus 4 squared minus 5. And then we're trying to plug this whole radical expression in here. So it'll be negative square root 1/3 x plus 5 minus 4. Okay, so how do you simplify this? Well, within these brackets, there's nothing that needs simplification, which means I can just take those brackets away and continue simplifying. And with those brackets gone, we see that we're now free to cancel the negative 4 with a 4. And now we're looking at 3 times negative 1/3 x plus 5 all squared minus 5. So here we're squaring a radical. It happens to be a negative radical, but when you square it, it'll be negative radical times negative radical. The negatives are still going to cancel. So we'll get this 3. The negatives cancel, then the radical cancels. So you get 1/3 x plus 5 minus 5. Then the 3 is going to just cancel with the 1/3, leaving you with x plus 5 minus 5. And those cancel. So we land on plain old x, like we're supposed to. So now we do it one more time, but this time the radical function is the outer function. So we'll go negative square root 1/3 parentheses bracket plus 5 close parentheses minus 4. So there's our outer function all set up. And then our inner function is the quadratic. So 3x plus 4 squared minus 5. Okay, so again, right away these brackets aren't really doing anything. Take them away. And then you know that the 5s will cancel out. So we're looking at, well, the 3 and the 1/3 will cancel out now too. Because now we're just distributing, or not distributing, but multiplying the 1/3 by the 3. So now we're looking at negative the square root of x plus 9 squared x plus 4. I knew that thing would eventually trick me. Okay, so what happens from here? We're taking the square root of something squared. So that means it's going to cancel. We're going to get what we get. All right, and here's where we got a little stuck in class trying to talk about what the heck just happened. Well, what domain are we restricted to? We're not taking the x's that are greater than negative 4. We're taking the ones that are less than negative 4, right? So that means that when I plug in a value less than negative 4, we're getting something negative. We're squaring it to get a positive. And then we take the square root to get a positive. So how do I make these things come out positive like they're supposed to? Well, I can't use the absolute value bars because that would complicate things and everything would go haywire. So thinking this through, for an input like just whatever, negative 10, that's certainly less than negative 4. Well, negative 10 wants to give me negative 6, squared wants to give me 36, take the square root of that and I'll get 6. But then you make it negative to get negative 6, and you take away 4 to get negative 10 again. So what's happening here? Well, I don't think my output is the same as x plus 4. Because when I plug in negative 6, right, I'm getting... Sorry, when I plug in negative 10, I get negative 6. And I square that, it goes to 36. Then I take the square root and I get 6. So I've plugged in negative 10, and I'm supposed to get back positive 6. But when I plug in negative 10, I'm getting back... what? I'm getting back negative 6. So I can't clean that up with absolute value bars, though, because the absolute value bars won't resolve, and I won't be able to cancel the stuff I'm supposed to cancel. So you're just kind of supposed to know that for the inputs I'm allowed to use, this doesn't really match. I'm not actually going to get x plus 4 out of this. I'm going to get the opposite of x plus 4. So that means you kind of got to put a negative on this thing. You kind of just have to know that for an absolute value function, 1/2 is sort of hunky-dory, everything is positive and it works the way it's supposed to work, but the other half is the opposite of that expression. And this is that time, because we're working with the things from the left. Again, thinking it through, when I plug in negative 10 and do the math, I get negative 6 squared is 36, and then square root of 36 is a positive 6. But once I do the math and just say it's x plus 4, negative 10 plus 4 is negative 6. I'm not trying to get negative 6, I'm trying to get positive 6. So adding a negative here will sort of fix that. And of course, adding the negative also has the side benefit of making the rest of the problem work, because suddenly now you can cancel the negative with the negative that we had to add just to obey the math and obey our restricted domain. But those go away now. You get x plus 4 minus 4. Now you can cancel those, and now you land on x. But what the hell happened here? We had to add a negative. It's all pretty, weird. The algebra doesn't really exist for what we just did. We just had to kind of know that just canceling isn't really quite right. Just canceling doesn't give us a rule that models the situation correctly. We really want the opposite of that expression. So you do it, and then everything works out fine. I know that's weird, and this is like my 8th time trying to explain it, and maybe I'm not getting any better at explaining it, but hopefully it kind of makes sense why we need that negative. Anyway, I'm done. So that's number 12 done. I think I owe you a 15 too, so I'm going to work on that now too. See you later. Bye.